Hi everybody. We are still have to finalize this example with the polymer. Okay. We reached the following result, I think. What was our result? The result went as follows. Have I written it somewhere, somehow? I don't think so. So we know that Lx average, Lx is the extension of the polymer. It is A average Nx plus minus average Nx minus. Now we used the indicator function technique by saying that Nx plus is just the sum over I goes from 1 to n. N is the number of monomers that we have inside the system. F of I. Okay? F of I, where F of I is the indicator function. It is 1 if points in the x direction, and it's 0 otherwise. Okay. Now, the average of a sum equals to the sum of the averages, so Nx plus average equals to a sum I from 1 to n, the average of Fi. Okay. And here, this average, it's easy to compute because you're looking on one particle at a time. They're all completely independent and statistically identical. So it's just n multiplied by f of 1 average, and f of 1 average, it is e to the power, it is 1 multiplied by e to the power minus, or it's going to be plus beta mga divided by z1. Okay, so let's write down Nx plus average. It is simply n multiplied by e to the power beta mga divided by z1. We do exactly the same for exactly the same procedure for Nx minus. Okay. And we obtain that Nx minus average equals to, so we have here an A also, equals to A n e to the power minus beta mga divided by z1. Okay. So in total, what we obtain, that Lx average equals to A multiplied by n divided by z1 multiplied by 2 hyperbolic sinus of beta mga. Okay. I just added this result and subtracted from this that. So Nx is without an A, I'm sorry, L is with an A. Okay. And this guy minus this guy multiplied by 2, divided by 2, it's sinus, hyperbolic sinus, so we have this prefactor of 2. All right, and the idea was to take this result and compute the derivative with respect to mg. Right? So we want to compute dLx average to dmg, okay, of d to the dmg of 2an divided by z1 hyperbolic sinus of beta mga. Okay. So I remind you, z1 is the partition function of one single effective particle. which was e to the power minus beta epsilon multiplied by 2 plus e to the power minus beta mga plus e to the power beta mga. Okay. Now, I take this derivative. First of all, in this derivative, I don't really care about 2an, right? So d Lx average to dmg equals to, we have the prefactor of 2an. Now we have the derivative of hyperbolic sinus is cosinus, right? So it's cos of beta mga multiplied by what? I'm taking the derivative with respect to mg. So this is beta multiplied by a, not yg. Think about it in the following sense. Okay. If it bothers you, think of all of this. I'm replacing mg by tau. Okay, so this is mg. So if I say mg equals tau, okay, so what I need to write down is d Lx to d tau, which is d to d tau, and everywhere I write instead of mg, I write tau. So I have 2an hyperbolic sinus of beta a tau divided, I take this guy and I replace everywhere where I have mg, I replace it by tau. So it is 2 e to the power minus beta epsilon plus e to the power minus beta a tau plus e to the power beta a tau. Okay. So let's forget about mg because it seems that you don't like mg. So I have this derivative beta tau a multiplied by the inner derivative or derivative of inner function, which is beta a, divided by what we have in the denominator. So we have 2 epsilon minus beta epsilon plus 2 cosine, hyperbolic cosine of beta a tau. And now we have plus 2an hyperbolic sinus of beta tau a multiplied by the derivative of 1 over whatever we have over here. So it is minus 1 divided by, let's take another marker. So it's minus 1 divided by whatever stands in here to the power 2. So it's 2a e minus beta epsilon plus 2 hyperbolic cosine of beta a tau to the second power. Okay? And the inner derivative, we don't care about this guy. Do we have an a? We don't have an a over here. And what we have inside, it is just derivative of 2 cosine. So it is, what is the derivative of hyperbolic cosine? Sine. 2 hyperbolic sinus of beta a tau multiplied by beta a. Okay. So this is the nasty expression that we have. And in order to finalize it, usually when the forces are strong, I don't really know if the response is elastic or not. But I do know, okay, I do know that I am expecting to obtain an elastic result when the effective force that I'm applying, my mg, is small, right? So I'm applying a small force, I will get a small extension. And the elasticity modulus is the proportionality constant that stands over here. Okay, so all of this is nice, But usually when not usually, but always when I compute the elasticity modulus, this proof relation, I want to compute d Lx to d tau in the tau going to 0 limit. Okay? So this is, yes, this is an ugly expression over here. Okay? But in order to compute something, we actually need to take the tau to 0 limit. Okay? Now, what happens when we take tau to 0? So look on this. So we have cosine over here. We have cosine, hyperbolic cosine over here. We have a sine, and we have another cosine over here. And here it's actually another sine. Okay, so we need to understand what happens to cosine beta tau a in the limit when tau goes to 0. We need to understand what happens to the hyperbolic sine of beta tau a when tau goes to 0. Okay. Those are the two limits that we need to compute. Okay, so let's start with the cosine. What is the limit of cosine when tau goes to 0? So write it down as an exponential, right? So it is e to the power beta tau a plus e to the power minus beta tau a divided by 2. Since we are interested in the small tau limit, we expand each of those exponentials up to what? We expand it up to the second order or the first order derivative, right? So we're going to have, this is 1 plus beta tau a plus 1 minus beta tau a divided by 2. Okay. So it is just simply 1. Okay. Now the next order is going to include contributions from tau, okay, which is something multiplied by tau squared probably. I don't really care because tau is very small, so tau squared is going to be extremely small. I'm usually going to neglect all of this. Okay, let's look what happens in the limit. Okay, so here tau goes to 0. In the limit, the same limit, what happens to the hyperbolic sinus? So hyperbolic sinus of beta tau a, it is, okay, so it's the same. E beta tau a, just instead of plus we have a minus, e to the power minus beta tau a divided by 2. Okay. So it is 1 plus beta tau a minus 1 minus beta tau a divided by 2 again. Okay. So this is in the limit, then tau goes to 0, which equals to 1 over here cancels 1 over here, and we are left with beta tau. Okay. So those are the two limits, okay, that we are going to use instead of all the cosine and instead of all the hyperbolic sinuses that we have in our expression. Because the elasticity response is only expected, so why we are taking tau to 0 limit, elastic response is expected only for small modifications. This is the part of linear response. When I apply hard force, so when I'm pushing a little bit on this wall, it pushes me backwards with something which is proportional to, or the extension of the wall is going to be proportional to the force that I'm extending on it. Okay? But if I push the ball extremely hard, I will break it. Right? So the linearity is broken, and it's only kept linear. This linear response, it only applies when my forces are small. This is why I'm looking on the tau to 0 limit. Yes?
Your force is dependent on the weight.
Yes.
The polymer.
Yes.
Why can
Not the weight of the polymer, the weight of the mass.
the mass is what?
The mass, external mass that I'm attaching to the string. It's not the weight of the.
Why can you assume this mass is really small?
Why not? I put it over there. Right? I put it over here. Can be very small. Right? So if it was the weight of the polymer, yes, you're completely correct. But in all of this, the masses, small masses, were extremely small. I neglected just how the mass of each monomer is actually affecting anything. Great. We substituted everything inside. So what do we have? We have this dlx to d tau in the tau to 0 limit equals to. Let's look on this guy. So we have 2an. We have this cosine, which is 1. We have beta a. We have 2e minus beta epsilon plus 2. So this term is simply 2a n beta a divided by 2 e to the power minus beta epsilon plus 1. This is the first term. Okay? What is the second term? The second term is going to be negligible. Why is it going to be negligible? Because, well, we have a minus, right? Now, and we have 4 over here from this guy and from that guy. So we have minus 4 a n. We have beta a. And here we have the second power of the hyperbolic sinus. The hyperbolic sine is beta tau a. Okay? So this is going to be beta tau a squared, okay, divided by whatever stands over here. What stands over here? It is just 2 e to the power minus beta epsilon, and cosine is 1. Okay, so it's the second power of 2 e minus beta epsilon plus 1 to the second power. Okay, so somewhat ugly expression.
Oh, the square should be on everything.
The square should be on a, yes, you're right. The square, it should be over here. Okay. But it doesn't really matter. Why? Because here, this guy is independent of tau. It depends on epsilon, and it depends on the temperature, on the number of monomers. It depends on the intrinsic properties of the monomers and the polymers. Right? This guy is going to be dependent on tau, which is actually the mass or the force that I'm exerting on the system. So the smaller mass I'm putting, or the smaller the force that I'm exerting on the system, smaller this guy is going to be. And actually what's interesting is not this negligible contribution, we don't care about it. Okay? The only thing that's interesting is this guy. Okay? And that's it. So we can write down that dlx average to d tau in the limit of tau goes to 0, which is the interesting and important limit. We have, now let's write down all of this without the beta, but we use the temperature. So we have 2a squared n divided, so 2 cancels out, so a squared n divided by k Boltzmann t, and here we have 1 plus e to the power minus epsilon divided by k Boltzmann t. Now this is interesting. So first of all, we can calculate it, and from this expression, by modifying the external force, we can find out what are the different MEs, what is A, what is epsilon. But actually we also see that the behavior of the monomer is interesting, because what is dlx d tau? So remember, we said that Lx minus L0 equals to some k multiplied by force. In our case, k tau. Okay? So this, in the limit of small forces, this is this k. This is the response to the external force. Okay? So I apply a force and I look on the average extension. Okay? And about how much, so this is like a spring constant. Okay? The larger k, the larger is the extension, or the larger is the response to the applied force. Now, if we plot this K as a function of temperature, time of temperatures, we'll observe this, 1 over TdK. Is it reasonable? Right? So I increase my temperature, and the response becomes smaller and smaller. So what will happen to a regular spring? If you go to a lab, you take a spring, okay? You compute the spring constant by measuring the extension of the spring when you put several masses on it. Okay? Then you heat up the string. What do you expect will happen? The regular spring. What do you think will happen? So what I will expect, okay, usually with a simple spring, that the more I heat it up to some very high temperature, the more I heat it, the larger the extension is going to be. The larger K is going to be. Why? Because the different molecules are more loosely connected to each other. Therefore, it's easier for me to extend the spring at higher temperatures. It's the other way around for our model of the polymer. Why it's so? It is so because the model of the polymer, it's not a one-dimensional thing. Okay? It's 2 dimensions. Okay? So I will remind you what we had. We had a bunch of monomers connected to each other, okay, that have to pay a specific price in order to be oriented not along the x direction. Okay? This is my polymer, my model of a polymer. What happens when I increase my temperature? So remember, the price that each monomer has to pay in order to be oriented not in the x direction or minus x direction, it is e to the power minus beta epsilon. Okay. There isn't some specific epsilon, and if I want to be oriented not along the x direction, I have to pay this price, energetic price. Okay. So therefore, if I don't attach any spring, any force to it, and even if I attach some force at the end of the monomer, some mass, not a force, what will happen is that the majority of the particles, the monomers, will try to be in the x direction. So I apply this force, and the thing goes in the direction of the force. But when I increase my temperature, okay, this price is becoming smaller and smaller and smaller. Okay? So each monomer starts asking the following question: yeah, I prefer to go in the x direction or the minus x direction. But if the temperature is very high, the probability to be in the x or minus x is almost equal to the probability to be in the plus y or minus y. So instead of having something pretty ordered, that will be the preference in the x direction, for high enough temperatures, I will have something which is extremely complicated. Okay? And I'll try to pull on this complicating thing because it doesn't have any preference to go over there or over there. The response is going to be smaller because many more particles are going to be oriented in the y direction and not in the x direction. Therefore, we see this dependence on the temperature. The response is getting smaller and smaller as we increase our temperature. Okay? So this is counterintuitive when you think about it as a simple spring, but it's not a simple spring. Okay? It is something that have several degrees of motion, and the moment that we include those several degrees of motion and make those probabilities of explore those additional degrees of motion, the whole system doesn't behave as a simple spring, behaves differently. Okay. Very nice. Okay. Any questions about the polymer example? Because we are moving forward. Yes?
Can you explain again how we go from what's in red to the bottom line?
From here to here, I just neglect this. Put a big X on it. Now, you see the dependence, the square dependence on the tau. So in the small tau limit, it's a negligible component. That's it. Okay. Other questions? Yes.
אפשר אולי להסביר שוב כאילו ככל שהעלינו את הטמפרטורה קיבלנו אפסילון יותר גדול?
No. So the question is, the explanation is as follows. So in order to go up, you have to pay a price because your probability, if you're going up, is going to be proportional to e to the power minus beta epsilon divided by z1, right? The higher the temperature, the closer this thing to 1, right? So we have e to the minus epsilon divided by k Boltzmann t. When I take t to be large, all of this is going to be like 1. Okay? So the probability to go in this direction is actually going up with temperature and not down. That's it. That's the explanation. It's exactly the same, yes. This is why also, so think about it. Everything becomes equally probable. X minus x, y minus y. The same argument works over there. This is why the response is bad. This is why the response is bad. If the temperature is low, I have a specific direction where the probability is going to be proportional beta or m g a divided by k Boltzmann t. When t is small, this is extremely large when you compare to the other three directions. Therefore, I prefer to be in this direction, okay, and therefore the response is large. That's it. Okay. Other questions? Great. So let's continue to the third example, which is going to be extremely long and includes several steps. And this is, well, and it will include some different concepts of how to calculate partition functions and etc. etc. So, and in general, I will call it specific heats or heat of solids. Okay. Question, yes?
Is there really a material that gets stronger when you heat it up?
Strong, what do you mean? Yes. Yes. What do you mean by stronger? It just crumples around and you try to pull. So yes. Take a polymer and it will behave exactly like that. Forget a polymer. Take a telephone cord, do something like this and try to pull. It won't open, right? Same idea. It's not working for one-dimensional systems because in one dimension it's already one dimension and you only care about the x direction in the first place. The moment that you include in your considerations additional dimensions, so the probabilities of being in the y direction, the whole thing can become extremely crumpled around with a lot of knots, okay, because of the temperature. And when you try to pull on it, it won't. So it's all about dimensionality and exploring your phase space. That's it. Okay, so I want to introduce to you a riddle. Well, it was a riddle up till 100 years ago or so, even more. And it's related to the behavior of specific heats of a solid. So you take almost any solid, okay? You take any solid, you heat it up, okay, and you measure the amount of heat, the amount of energy that you have to put in order to increase its temperature. So this is how you compute the specific heat. Okay. So you want to calculate the specific heat of a solid. And you have many different solids. Okay. So this is your CV. And here you have your temperature. And surprisingly, for almost all the solids that you measure, you have very universal behavior. In what sense? First of all, for high enough temperatures, your solids or the specific heat will converge to a constant. Not just any constant, but very specific constant. Okay? We'll describe what this constant is. Okay? This constant, okay, so it's the convergence to a constant for high temperatures, and for low temperatures, the convergence towards zero, because the specific heat has to be 0 for t equals 0. So the convergence to 0 goes as t to the third power. Okay, so we have a general constant, universal constant, let's say as follows. So CV divided by the size of the system converges always to the same constant. Okay? And the decay towards 0 for almost any solid goes proportional to the temperature to the third power. Okay? You take one solid, this is what you get. You take another solid, this is what you get. In between, okay, they differ from one another. So in this region, it is not exactly uniform. It always looks like this, but not exactly. One solid can be a little bit up, the other solid is going to be a little bit down, but there are two universal limits: high temperatures, okay, and low temperatures. Okay. So if you take almost any solid, this is what you see: convergence towards a constant, and for high temperatures, universal constant, and convergence towards 0 with a specific power law. Okay. And this is a riddle why it's behaving. So physicists always like universality. Why? Because, well, it's some part of our religion called physics. We believe that there are general laws that control the universe, and those laws are applicable everywhere. Okay? For example, two charged particles are trapped in each other, and the Coulomb law is very universal no matter where you take those particles' charges from. Okay? The same goes over here. So something very interesting, well, or universal, occurs for high temperatures and low temperatures. Now, moreover, this part of our religion says, well, when you have universality, usually you have a very specific reason why it's universal. We can call that, in this limit, there is something very special, okay, this universal law that applies, and this is why we see this constant. And in this limit of small temperatures, there is also something very special that is applied everywhere, and this is why we see this t to the third power. Okay? So almost any system that we look upon in physics, we try to understand the behavior as part of a very global phenomenon. Okay? So when physicist looks on this and says, well, if I do have this universal behavior for many different species, many kinds of solids, okay, I know that there is some universality or some general laws applicable over here, applicable over there. The thing that I have some non-universality in between, well, because life is complex and maybe those two general laws have somehow mixed between each other in the middle. This is fine. Here I have some separability, and only one reason why it's behaving like this, and another law over here. Okay. So this behavior troubled physicists more than 100 years ago, and around 1912, 1914, I think, were made the first attempts by using statistical physics to solve this puzzle. Okay. I don't like this marker. So what we are going to do from now on and today and next week, we are going to try and apply what we know from statistical mechanics, basically the canonical ensemble approach, towards solids and simple models of solids, in order to explain what happens here and what happens over here. Okay? So, what we are going to do, we are going to explain why it's universal over here.
What was the problem?
The problem is why, if I take this solid and I take this solid, which are very different, I measure their heat capacity, and in small temperatures they behave the same, and at large temperatures they behave the same, although their molecular structure is very different.
You mean that all solids share a similar behavior?
This is what is called universality. The same behavior for very diverse systems. Yes?
How is it possible?
I don't know. Well, you will see. Okay? You will see, right? But how it's possible that this guy and that guy attracts each other according to a general law of attraction, okay? And the sun and the earth also attracts each other exactly by the same law. Seems not reasonable, but it works, right? So we believe, and this is what I call it, part of our religion, that there are universal features that are applicable everywhere. And when you look on this and say, oh, there is a new feature. There is a new feature. I have to find out what it is. Okay. This is why it's interesting. So it's interesting to understand, okay, so this material, how exactly it works. But in my perspective, and this is the usual perspective in physics, is it's much more interesting to understand something global. Okay, that's not as applicable to my very specific material, but it's also applicable over here and over there and over there. Okay, so the first approach, and this was done by the master of simple models, which you know by the name of Albert Einstein, is to use a very simple model, Gedanken experiment. So Einstein has already published his papers, he's very famous, and he knows something about the photoelectric effect. So he has those ideas about specific energetic levels, okay, when he approached this thing. No quantum mechanics yet, right? So we're talking about 1912. And he tries to understand this in a very simplistic form. And the idea of Einstein is as follows. Okay, so what is, it's after Rutherford experiments, okay, so we know that there are atoms, right, which is kind of a new thing back then. So when we think about it, so he said the following thing. Look, so I have a solid. So what is a solid? It is a bunch of particles. And I know that in a solid, those particles are sitting in some very specific structured nature, way. Right? So let's assume that this is my solid. It's a very simple one. Let's look on each and single particle over here. Now, I know that when I heat up the system, this is what happens when I'm trying to compute the specific heat. Well, the particles somehow they rattle a little bit more, okay? Or when I cool this down, they rattle a little bit less. Okay? But overall, what I know that there are 3 degrees of motion, okay? That's reasonable, for each and single particle. Okay? So it can have a degree of motion in the x direction, in the y direction, and let's assume that this is the z direction. Okay? Great. Now, moreover, okay, so I cannot assume that solid is just a gas, right? It's unreasonable, it's too easy. Well, we sometimes do this, but it's too easy. So the next level of simple thing or simple model is to assume, well, let's assume that each of those particles is behaving as a harmonic oscillator that oscillates in the x direction, in the y direction, and the z direction. Okay. So the more it oscillates, the hotter the system is, the less it oscillates, the cooler the system is. Okay. So each particle is a 3-dimensional oscillator. Now Einstein was smart. Okay, so he initially said, well, there are of course some interactions between all the different particles, all the different molecules inside my system, but well, I don't want to work hard. If you read Einstein's papers, he never works hard. It's just some type of genius thinking of simplification. So he assumed here something that, well, all the particles, all the particles are independent. Okay. So it's a big simplification, right? Because now why this assumption comes in, I explained to you. Well, we cannot assume that it's a gas, but it's not a gas. It's harmonic oscillators. But the independence assumption is crucial. Why it's crucial? Because in statistical physics, well, at least what I taught you so far, we only can solve problems where the different components of the system are independent from each other. Otherwise, we don't know how to build this partition function. Okay? So Einstein, in first place, says, well, I would take them as independent. Why not? And let's see what happens. So this is, well, this is what is known. Einstein model of solids. Now, this is of course not enough, right? I told you that Einstein already published his paper on the photoelectric effect. He says also the following thing. Well, light can have quantas of energies, right? So particles can also have quantas of energies. Okay. So if I look on the energy,
This is before quantum mechanics.
this is before quantum mechanics, but after photoelectric effect. Who is the father of quantum mechanics? Yes, because he thought about the discrete space, discrete states, and that has quantas of energy.
Used to accept it very.
This is a big riddle. Why? Yes. Yes, but the same idea follows several of his works. He, as you said, he refused to accept quantum mechanics, maybe theologically, but he always used those quantas of energies in whatever, if he wanted to. So, okay, so energies of each degree of freedom. So it is equals to some number n multiplied by h bar multiplied by the frequency. It worked for photoelectric effect, right? So why won't it work for solid?
Because you need to. I think you need to have half.
So you have an additional one, right? Plus whatever. He has no solution yet about the exact solution of the harmonic oscillator. Okay, and in anyhow, this is a constant addition, so you don't get it. Okay. So Einstein was not using those addition of 1/2 h bar 0, h bar omega. This is the assumption. Now, what I mean by degree of freedom, you look on each and single particle, and we say it's a three-dimensional harmonic oscillator. So in the x direction, the particle oscillates harmonically, and it have different energies and h bar omega. In the y direction, it also oscillates harmonically. It's going to have different n, but also n h bar omega. And for z direction, it's going to have a different n. So each particle have an x, and y, and nz. Okay. Quantum numbers, what we call them nowadays. So you have three quantum numbers for each particle, and they're in total n total number of particles. Total number of particles. Okay. So by using Einstein assumptions, right, we can say the following thing. This is the whole model, right? So it's very oversimplified reality, but this is what we do in physics. We try to simplify things. Okay? So in Einstein representation now, because all the different particles are independent, and the different degrees of motion for each and single particle are also independent, we come down to the following description of the Einstein model. We have 3n particles, right? So I don't care if it's particle of a degree of motion. You can call it quasi-particle if you like, you can call it effective particles, but I don't care. So this is degree of motion. It contributes to the total energy as n h bar omega. Since this guy is independent of that guy, well, they are different particles for me. So we have 3n particles, independent, and each of those particles, for each particle, the energy equals to n h bar omega. Okay? So it's very similar to the two-level system, but it's actually infinite number of level systems for each particle. This description simplifies a lot. The moment that I write it to you, I expect from you to say, oh, I know exactly how to solve it. I will compute the partition function of a single particle and then take it to the power of 3n, and that's it. Why? Because they are independent. Okay? So remember, any time that I want to address a question in statistical mechanics, specifically I want to compute the partition function, because the moment that I know the partition function, I know everything. Okay? So the problem is I need to see that the total energy is additive, and I need to have independence of different contributions to the energy. Those are the two requests in my prescription. So the total energy, it is the sum over I goes from 1 to 3n of ni h bar omega. Why? I'm going over each and single particle, but I'm not counting now particles. I'm going on each and single degree of motion, and I know that the contribution to the total energy of all the different degrees of motions is like this. I just have different numbers. Like for a single particle, I will have n, x, and y, and z. Now I have n1, n2, n3, n4, n5, n6, etc., etc., etc. Okay. So first of all, we see it is additive. Check. The next thing is, well, are all the different ni's, are all the different contributions here are independent? Check. This is part of the assumptions that Professor Einstein did more than 100 years ago. Great. The moment that those two things are in order, I know how to proceed. I know that I will compute Z1, and Z is going to be Z1 to the power of the total number of particles. How many particles I have? 3n. So it's going to be Z1 to the power of 3n. What is Z1? Remember what is Z1? So I'm going from n1 goes from 0 to infinity, e to the power minus beta. And here I put the energy of, or possible energies of this degrees of freedom. So it is n1 h bar omega. This is Z1. What is this?
Geometric sum.
This is a geometric sum. Okay? So we have e to the power n1 goes from 0 to infinity, e to the power minus beta h bar omega to the power of n1. And this equals to, the first term is 0, n1 equals 0. So this first term in the sum is 1, divided by 1 minus whatever we are multiplying, which is minus e to the power beta h bar omega. Okay. So Z is 1 over 1 minus e to the power minus beta h bar omega to the power of 3n. We are done. Okay. You can compute other stuff from now on. That's basically it. Okay. Very, 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 very simple. Now, let's see if it works. Right? So remember, we have two limits. One is high temperatures. The other one is low temperatures. So the quantity that we want to explore, it is CV. Okay. Now CD, it is du to dt. U is the average energy. So we have two ways of doing this. Either we remember all the formulas from our formulas sheet. So basically we say, all right, so I can calculate the free energy, and it is -1 over beta log of z, and then I can take out of F and calculate U. Okay? So you have to take some sort of a derivative of F with respect to beta, etc., etc., etc. So that's it. Now, instead of doing that, because I never remember all these formulas, you can say, well, let's compute U directly. Okay? How would I do that? Why or how? What is U? What is it? When I say to you that CD is du to dt, what is U? Average energy. I need to compute the average energy of the system, okay, and take the derivative of the average of the system, the average energy of the system with respect to the temperature. Now, so again, you can use the formulas that you already derived during thermodynamics class, or you can say the following. What is U? U, okay, U is the average over the whole system. Now, because the general energy of the system is the sum of the energies of all the different parts, okay, I can say, exactly as I've done for the polymer model, I can say that U is 3n multiplied by U1. What is U1? Exactly. The average energy of a single particle. Why? Because they're all independent. I compute the average of one, and then I know the average of any one of them, so I just need to multiply it by 3n. Okay? So again, using this trick that the average of a sum is the sum of averages, and that's it. Okay, so how I compute U1. This is easy because, well, U1, it is a sum. I goes from 1 to U1. So it is n goes from 0 to infinity. Here we have n h bar omega, so this is the possible energies that the particles can have, multiplied by e to the power minus beta n h bar omega divided by z1. Okay, so this is the values that the energy of each and single particle can obtain, and those are the probabilities of those different states. Okay. Possible energies, probabilities. Okay. Great, so I just need to perform this summation over here. What I do in order to sum, so first of all, I take out z1 out. So I have 1 over z1, a sum n goes from 0 to infinity of n h bar omega e to the power minus beta n h bar omega. Okay. And here I use the Feynman trick. Do you know what's a Feynman trick?
Yes.
Yes. No. Okay, so what for me is a Feynman trick? Feynman trick is usually applied, it's also called the Lifshitz rule for integrals. When I have an integral or I have a summation, I represent whatever I need to sum as some kind of a derivative with respect to a different parameter. Okay, so when I look on this thing, I notice that n h bar omega e to the power minus beta h bar omega, it is exactly as minus d to d beta of e to the power minus sorry, there is an n over here, minus n beta h bar omega. Take your derivative with respect of beta of this guy. So we have minus that's come downwards, so it kills the minus, and we also have n h bar omega. Okay, why it's useful? Right? Because when I put it inside, so I have 1 over z1, a summation n goes from 0 to infinity, minus d to d beta over e to the power minus beta and h bar omega. Okay. What a regular physicist will do when he looks on this sum, what would you do when you look on this sum? What is your next step?
I will move the derivative outside.
You will move it. Anyone else will move the derivative outside. Who won't move the derivative outside? You. So you're the mathematician, right? Why? So the mathematicians will start to ask questions like, can I move it outside? Why won't I move it outside? Etc., etc. And then we'll prove a big theorem that will say, if the sum is uniformly converges מתכנס במידה שווה to something, then I can take the derivative outside. What a true physicist will do? We move the derivative outside without asking a lot of questions. Okay? It works until it doesn't. Okay? So it's 1 over z1 minus, we took the minus over here. Here we have d to d beta, and here we have a sum which is n goes from 0 to infinity e to the power minus n beta h bar omega. And this is z1. Okay, so what we have is minus 1 over z1 d to d beta of z1. This is a general formula. It always works. It always works because of the Feynman trick. So you don't have to develop it each time. You can just remember, or you can develop it easy. All right, so we know what is z1. Okay, so let's take the derivative. I remind you, z1 is 1 over 1 minus e to the power minus beta h bar omega. Okay, so d to d beta over 1 minus e to the power minus beta h bar omega is what? So it is minus 1 divided by 1 minus e to the power minus beta h bar omega to the second power. And then we take the inner derivative of this guy, which is minus e to the power minus beta h bar omega, multiplied by what?
By h bar omega.
By h minus h bar omega. Okay. Okay, so let's now put all of this inside this expression. We obtain that u1 equals to minus 1 over 1 minus e to the power minus beta h bar omega multiplied, so we have minus 1 minus and minus, so we have 3 minuses over here, and we have 1 minus from here, so let's delete it. Okay. So we have e to the power minus beta h bar omega multiplied by, we put the additional h bar omega over here, divided by 1 minus e to the power minus beta h bar omega to the second power. I can cancel out this guy and the second power. So therefore, u1 equals to h bar omega e to the power minus beta h bar omega divided by 1 minus e to the power minus beta h bar omega. The first thing that you check whenever you finish something complex, are the units right? Right. Unitless, units of energy. H bar omega, it's units of energy. Okay, so at least the units are correct. Okay, so we know that the total energy, the total average energy is 3n h bar omega e to the power minus beta h bar omega divided by 1 minus e to the power minus beta h bar omega.
Now we want to take beta SK volts.
Yeah. So the next step, right? Remember, CV is to take d to dt of u. You cannot escape in this class from taking derivatives and taking integrals, etc., etc. It will always be part of the lecture, and it will become longer and longer as we enter the semester. Okay, so this is what we have. This is u. Let's take, so we need to take d to dt of 3n h bar omega e to the power minus beta h bar omega divided by 1 minus e to the power minus beta h bar omega. So, you know what, I will say, let's take the derivative with respect to beta, and then take the derivative of beta with respect to t. Sounds fine?
Yeah.
Yeah, so I have this to d beta of this guy, multiplied by d beta to dt. That should work, right? Where you have additional beta? So I can, so you want me to write it down as this guy, e to the power beta h bar omega minus 1. Fine, it's also good. Yeah, good suggestion. Okay, so we are taking the derivative with respect to beta of this guy, and then we multiply it by d beta to dt. Okay, so the derivative of this guy, we have 3n h bar omega multiplied by minus 1. What we have from here, it is e to the power beta h bar omega minus 1 to the power of 2, multiplied by the inner derivative, which is e to the power beta h bar omega, right? Multiplied by h bar omega. Okay, so this is this part. Now d beta to dt is what? Let's write it down over here. D beta to dt equals to d 1 over k Boltzmann t to dt is minus 1 divided by k Boltzmann t squared. Okay, so we minus 1. Let's write it down as minus 1 k Boltzmann t squared. Okay, so minus 1 cancels out, which is good. Why is good? Because we expect that the heat capacity is going to be a positive quantity. I heat the system up, the energy of the system goes up. I don't want to heat the system up and get the energy is actually getting less, smaller. Let's write it down, this final result over here. So what we have, k Boltzmann t, this guy stays the same, so we have 3n, so CV, it is 3n h bar omega squared. Here we have e to the power beta h bar omega, e to the power beta h bar omega minus 1 squared divided by k Boltzmann t squared. Okay, so that's it. That's it. Okay. So now this is the final expression. It's not so ugly. Okay. Remember what was the riddle? The riddle was I have an approach to a constant for high temperatures, and I have a very specific shape when the temperatures are going to 0. Okay? So we need to find the limit of this behavior for high temperatures and for the low temperatures. Okay? So CV goes to when t goes to infinity. This is the first limit. And the second limit is when what happens to CV when t goes to 0. Okay? Two different limits, but the claim is there is universal behavior over there. Can we get this universal behavior from a very simple approach of Einstein? So let's see. Let's take this limit first. Do it over here. And so you already seen how I approximate stuff when I have different exponentials. So at the beginning of this class today, we had, instead of temperature going to some value, we had the force going to some value, but it's basically the same idea. You look on this guy and you say, well, where I have the dependence of the temperature. So T is going to be extremely large, right? So what I have here is that I have e to the beta h bar omega, okay? And I want to see where it goes as t goes to infinity. Okay? Because I cannot approximate this guy to already have a t. Those are constant with respect to the temperature. So the only thing that it's not constant are those exponentials that appear over here and over here. Okay, so it is e to the h bar omega divided by k Boltzmann t. Okay, t goes to infinity, so this guy goes to 1. You know what? 1 is not good enough. Why? Because look on the denominator. So if I plug 1 inside over here, it will get cancelled by 1 over there, and all of this will explode. It's never a good idea to explode stuff. So we'll add the next term. What is the next term? Plus h bar omega divided by k Boltzmann t. Okay, so we see as t becomes very large, this term becomes more and more negligible. Okay, so CV goes as t goes to infinity. 3n h bar omega squared. For this guy, I can use the approximation where I take the exponential just as 1. Multiplied by 1. Divided by, I plug my approximation up to the first order in the denominator. So here I have h bar omega divided by k Boltzmann t squared multiplied by k Boltzmann t squared. Okay. H bar omega cancels out. T squared cancels out. I have 3 and k Boltzmann. So CV goes to, when the temperature is high, to something extremely universal. What is 3n?
The number.
The number, but this is like the size of my system, right? Okay, Boltzmann is a very universal constant. Okay.
שאלה.
Yes. A question.
איפה בכלל בכל התהליך הזה הכנסת שיש שונות בין מוצקים?
Oh, very good answer. Very good question. So where is I put inside my system there is some difference between the different solids.
The frequency of omega.
Sorry?
The frequency.
Oh, so I haven't, right? I have not, but let's see what will happen if I'll make some additional assumptions, like you see, that I make those different particles do something else. You know what will happen? The same result will reappear again and again and again. Okay? So what will happen that no matter how complicated you're going to make the Einstein model by introducing additional assumptions, this result that CV converges to 3n k Boltzmann will always reappear. Always. I will prove it to you later. Okay? But let's for a second stick just to the Einstein model. Okay? So for the Einstein model, okay, what we calculated so far So if this is CV, this is the temperature. And we divide it by the size of the system. In our case, the size of the system is, let's assume that this is N. Okay? Can assume that this is N. We know that this constant is just 3 K Boltzmann. And it's going to be the same K Boltzmann no matter what solid you pick up. Okay, so this is an experimental observation. As long as we don't do something really bad, if, for example, we get the solid through a phase transition, it's going to be not a solid but a liquid, so we don't liquidify it. Okay, this part solved. So we do understand something from the Einstein model. We do understand that in the limit of large temperatures, the particles don't care about each other. And this is what I said, that you can complicate the Einstein model as you like. At high enough temperatures, the particles don't care. They behave as just random oscillators which do not care about each other. And when you take this assumption and you put it in a very complex model, it will always provide you this result over here. High temperatures, particles oscillating somehow but they are not moving freely because it's still a solid. Those oscillations don't care about the neighbors at all. This is why you have a convergence to a constant. Okay? So basically, high temperatures, independence, this is what rules this behavior. And this is very universal. The more you heat, the less you care.
What about the low temperature?
Okay, great. So this is task number 2. This law, this approximation that we used over here, does not apply to the low temperature. So we need to approximate all of this somehow differently for low temperatures. So what happens at the other limit? We take this limit and we look again on beta h bar omega, which is e to the power h bar omega divided by k Boltzmann t. How it behaves when t goes to 0. How I will approximate it when t goes to 0. Can I approximate it by some other function? No. So in the limit of when t is 0, whatever is sitting over here in the exponent is an extremely huge number. So it's just an exponent of a huge number. There is no parallel approximations or simple approximation. It's just it. Okay, so we have e to the power h bar omega divided by k Boltzmann t. That's it. But when I look on this guy, I can say the following. E to the power beta h bar omega divided by k Boltzmann t minus 1.
Beta? H bar omega?
H bar omega k Boltzmann t minus 1 goes, when t goes to 0, I don't care about this 1 anymore, and it's simply e to the power h bar omega k Boltzmann t. So CV, in the limit of small temperatures, the only thing that I do, I just replace this e beta h bar omega minus 1 by e beta h bar omega, or the k Boltzmann t representation. So I have 3n h bar omega e to the power h bar omega divided by k Boltzmann t divided by e to the power h bar omega divided by k Boltzmann t multiplied by 2 because of the second power, and k Boltzmann t squared. It equals to 3n h bar omega divided by k Boltzmann t squared e to the power minus h bar omega divided by k Boltzmann t.
So when t is large, it's negligible.
What is the main contribution to this expression in the low temperature limit? Who is stronger? So 1 over t squared is diverging. Okay? So it goes actually to infinity. But the exponent converges to 0 stronger than any parallel. Okay? So we don't care in the limit when t goes to 0, we don't care about the t squared over here. We only care about the e to the power minus h bar omega divided by k Boltzmann t. So we have this limit. Okay, it converges to 0, and it converges to 0 as e to the power minus h bar omega k Boltzmann t. So Einstein got it wrong. Yes, his simplifications properly explain the large temperature limit. But the small temperature limit is actually, well, really wrong. It's not a parallel. It's not behaving as t to the third power. This is the experimental fact. You cannot argue with that. Okay? His simplifications were wrong. So somehow, somewhat, on the way, is wrong. Okay? So this is a very nice example. You take a model, you pick a natural behavior, you try to explain it by using simple physical models. You try to apply it. You solve a bunch of mathematical equations on the way, and then you fit the behavior to whatever theory you have in mind. Sometimes the theory works perfectly fine everywhere. The usual case is your theory doesn't work anywhere. Okay? There are exceptions where your theory works in some specific set of parameters, but it fails. It's not bad. It's actually good. Because you manage to understand something about the physics. Okay, so you say, well, since my theory works over here, my assumptions are correct. What were my assumptions? Independence and harmonicity of all the different particles. This is pretty pretty good idea to understand that for large temperatures, I have a bunch of different particles that are completely independent. Okay? What happens over here, we still have to find out. I have less than 10 minutes left, so we'll finish over here, but what we will continue is how a guy named Debye arrived and said, well, I know where Einstein was wrong. So we are going to extend Einstein model to something which is called Debye model, solve it. It will take us a lot of time, and we'll understand what happens in this behavior, in this limit. See you next week.
אפשר לשאול שאלות?
כן.